Recall the experiment performed during one of the lectures in which we flamed a piece of cotton by quickly compressing air in a closed reservoir. Assuming that initially air in the reservoir was at room temperature, T0 equals 20 degrees Celsius, and assuming that upon the compression the volume changed by a factor of 4, calculate the final temperature immediately after the compression. So what we've got here is a situation where we have a reservoir, some kind of box, containing some air, which is quickly compressed, so then the volume gets much smaller, and as the volume gets much smaller, the temperature will increase, and we use this to flame a piece of cotton. So we can draw a picture of a situation like this, where on the left is what we'll call state 0, and on the right will be state 1 afterwards, since we're given T0, our initial temperature over here. So we'll go with their naming convention of 0, and then following that we'll have state 1 after the compression. So in state 0, we know that the temperature is 20 degrees. So T0 equals 20 degrees Celsius, and T1, well, that's what we're trying to figure out. T1 equals, we don't know. And what else are we told here? We know that upon the compression the volume changed by a factor of 4. So the volume of the gas afterwards is 4 times smaller than whatever it was to start with. So we could call this here, just could label this as V0, and afterwards we can call it V1, or perhaps since we know that this is a quarter of the size, we could say this is actually just 1/4 V0. But now we've got a fraction here, and that just tends to get a little messier if we have fractions. So instead of calling this a quarter of the initial size, we could say that we'll just call this V1 and say that the initial situation over here is just 4 times whatever V1 is. So now what we want to do is set up some kind of equation that we can use to then find T1. Well, we're told that it is compressed very quickly, and we're also given here that this letter here, gamma of air, equals 1.4. So this gamma here is what we call the adiabatic constant of air. So we're given that it is 1.4. And both of these, us knowing that this happened very quickly, and the fact that we're actually told what the adiabatic constant is a hint that this is probably an adiabatic process. So if this is an adiabatic process, that means that no heat can enter or leave the system during the process. So as the gas is compressed, no heat is going to be transferred outwards to the surroundings. So all that heat or energy is going to stay within the system. Well, we know that an adiabatic process obeys the equation PV to the gamma equals constant. So that is the pressure times volume to some constant that we call the adiabatic constant. That always remains some constant. So throughout the process, the pressure and the volume will both change, but this will remain one fixed value. So that means that what we could say, considering state 0 to be the state before the compression and state 1 being after the compression, is that P0 times V0 to the gamma is equal to P1 times V1 to gamma, because this must always be a constant, so this must be true. Now, the question is asking us to find the temperature after compression, but we haven't actually got temperature in our equation here. But what we can always do though is anytime we have either a P, a V or a T, pressure, volume or temperature, we can rewrite one of those in terms of the other two by using the ideal gas law, which is PV equals N R T. The pressure times the volume is equal to N, the number of moles of gas we've got in our system. So that will just remain a constant because no gas is going to be escaping and no gas is going to be entering during the process. Multiplied by R, which is the universal gas constant, just a number that is always the same number in every equation. And T, the temperature. So we have P, but we actually want a T instead. So we can rewrite that P in terms of T by, let's divide both sides of this by V. And we get P is equal to N R T over V. And this will hold true for any state that we talk about in our process. So for state 0 or state 1. So we can then say that P0 is equal to N R T0 over V0. And the same thing would be true for P1 as well, just T1 and V1 instead. So let's rewrite our equation using this instead of P. So on the left hand side we'll have N R T naught over V naught, and then that's the P, and then we want this V naught to the gamma, and the right hand side will be basically the same but just with ones instead of zeros. So N R T1 over V1, and then we want to multiply that by V1 to the gamma. Now N and R are just remaining the same, so that we can divide both sides of that. So now N and R are constants, so we can just divide both sides of the equation by NR to cancel them. And now let's rewrite this slightly. Let's say we have T naught, and then we'll have a V naught to the gamma over V naught, but instead of doing a fraction, let's write this V naught down here as a V naught to the minus 1 instead. So that would give us V naught to the gamma multiplied by V naught to the minus 1. But also we can then rewrite this as, well, we know that anytime we have something like a to the x multiplied by a to the y, that would just be the same as a to the x plus y. Just have to add powers. So we can do the same thing over here. So instead we'll just add the powers, and this becomes gamma to the minus 1. And then we'll do the same on the other side, exactly the same. We have T1, and these two V's can just be simplified to V1 to the gamma minus 1. Okay, so now let's try to deal with the volumes. So what we did up here was we said that the initial volume is 4 times the final volume. So we can kind of write that a bit more explicitly, saying that V naught is equal to 4 V1. So then let's make that substitution, plugging 4 V1 into our V naught over here. That will give us T naught times 4 V1, and all of that will be to the gamma minus 1 power. So equals T1 V1 to the gamma minus 1. So what we can do then is distribute this power, because any time we had perhaps an a, b to the x, that would just be the same as a to the x times b to the x. So we can then rewrite that as t naught. Then we have our 4 to the gamma minus 1 and v1 to the gamma minus 1. And right hand stays the same, t1 v1 gamma to the minus 1. And now that we have a v1 to the gamma minus 1 on both sides, we can just divide both sides by that, they cancel. And also, while we're at it, we know that gamma is equal to 1.4, so therefore gamma minus 1 is just 1.4 minus 1. We can say that gamma minus 1 just must be equal to 0.4. So let's write this out again here, and we'll have, put the 4 out front, we'll have a 4 to the 0.4 power multiplied by t naught equals t1. And now we're just about ready to plug in to solve for t1, because we know that t naught is 20 degrees Celsius. But before we do, we need to first convert that temperature in Celsius into Kelvin, since all of these equations are sort of expecting us to give a value in Kelvin, and if we give a Celsius temperature, we'll get a different answer. So we have that T naught is equal to 20 degrees Celsius, but to convert that to Kelvin, we know that Kelvin is just Celsius plus 273.15 degrees. So converting that to Kelvin, we can just say T naught is equal to, well, 293.15 Kelvin. So then our final answer, just about, in Kelvin, we can find that with 4 to the 0.4 multiplied by 293.15 Kelvin. So we have 4 to the 0.4 multiplied by 293.15. So our answer in Kelvin would be 510.4 degrees Kelvin. But if we want to convert that back into something we can actually understand a bit easier, we can convert it back into Celsius by subtracting 273.15. So then we get our final answer for the temperature is 237.3 degrees Celsius. And there we go. So all we had to do for that question was firstly just recognize that it was an adiabatic process, meaning that we could use PV to the gamma equals constant, and then just write one of the volumes in terms of the other so they would cancel later on, convert our given temperature to Kelvin so we can actually plug it in, and then that gave us our final answer.